So I'd like to talk about how limits interact with our concept of infinity. There's a couple different ways this can play out. So just to be clear, what do I mean by infinity? Well, infinity is not a real number, right? There's no position on the x-axis that I'm going to call infinity. Infinity is an idea, and the way we talk about it is more or less just sort of convenient for lots of different but related ideas. So when I talk about positive infinity, I'm talking about the idea of like the very end, way, way out on the horizon, the end of the positive x-axis. The same way as you can never actually get to the horizon, it's always out there, you can never actually get to positive infinity. Or sometimes I'll just call it infinity for short. Negative infinity is the same idea, but for the negative half of the x-axis. It's the horizon point. It's all the way out there, but it's not actually a real number, right? Negative 1 billion. That has a large magnitude, sure, but it's not any closer to negative infinity than, say, -1 is. So these concepts exist for us to have easier ways to talk about things, about growth of functions, about values of functions, and we should pay careful attention to how to talk about limits and infinity. Makes sense. We want to make sure that the things we're saying make sense, even when the things we're saying are convenient shorthand. Now let's take as an example the limit of the function 1 divided by x squared. And I'm going to calculate this limit as x tends towards 0. Now, as x is getting smaller and smaller, I'm dividing by smaller numbers, which means that this, I'm thinking of this as a function, y equals 1 on x squared, that function is getting larger and larger and larger without bound. I can make it larger than 100 when x is 1/10 or less. I can make it larger than 1,000,000 when x is 1/1000th or less. I can always make this larger by taking smaller values of x. There's no bounds. So this diverges, right? This limit does not exist. There's no real number I can associate to this limit and have it be a sensible thing or even a useful assignment. Now, when I switch to the graph of this function, y equals 1 divided by x squared, I get this. So I picked the x squared because I have both sides of the function going off in the positive direction. That's a very nice thing for this demo. You might colloquially say that this function is going to infinity. And never mind the Buzz Lightyear stuff for right now. But that is a perfectly acceptable way to talk about this, and it's even the technical way to talk about this. So I would write limit as x approaches 0 of the function 1 divided by x squared equals infinity. Now this is a shorthand notation. Remember, infinity is an idea. It's not a real number. So this equation, this is shorthand. This helps us understand a very complicated idea and write it down in a short way. So what this actually means, and this is the generic form, so x is going to just some coordinate a, f of x is unspecified. This means that as x approaches the value a, the function f grows unboundedly in the positive y direction. So there's infinity on the y-axis as well. I can also talk about functions approaching negative infinity or their limit equaling negative infinity. Tongue twister, gosh. And this is the same idea. As x approaches a, again, the value of the function f of x grows unboundedly in the negative y direction. So again, we're going negatively, but the magnitude of this quantity is growing larger and larger and larger. -1, -10, -100, -1,000. Each one of these is less than, in the sense of greater than, less than, but their magnitudes are growing. And so that is the idea for limits which equal infinity. That just means the function grows unboundedly, like we can see in the picture. This picture here. So as x approaches 0, my y value grows without bound. It doesn't matter how far I zoom out, I can't actually see the whole picture. So that's what I mean by limit of f of x equals infinity.